This is part of the BocaPhysics series on electromagnetism. In today's lecture, I'm going to begin the discussion of radiation. And we'll look at one particular example, that of the oscillating electric dipole. We'll start where we left off last time around, and that's with Yeffimenko's equations. So the first expression gives us the electric field. It's a generalized Coulomb-Faraday law. Second expression gives us the magnetic field, the generalized Biot-Savart law. If you notice the first term, the charge density does in fact have dependence on T-Savart. T-Savart is retarded time, and retarded time is defined as T minus the magnitude of the separation vector over C. So T is the present time at where you're evaluating the field, and essentially you've got a time lag because of the time it takes the signal information to propagate from the source to where it's being observed. Now, in these next two terms, we have time derivative of the charge density and time derivative of the current density. So again, in the event that there is no dependence on time, these two terms will just be zero, and this first term just collapses back to the static Coulomb field. Now, for our Biot-Savart law, we've got the first static term. Of course, generally speaking, the current density does depend on the retarded time. However, the second term depends on the time derivative of the current density. And what you'll notice here is that there is no time dependence. The second term goes to zero, or is zero, and the first term just collapses back to the static Biot-Savart, or quasi-static, if you prefer to say it that way. One other feature I wanted to point out, notice the dependence on separation vector r minus r prime. This goes as, well, we've got basically a factor up there. So it's basically going at least as fast as 1 over r squared, and this is going to go as 1 over r and 1 over r. This is 1 over r squared at least, and 1 over r. So the question is, that we want to pose, first of all, is what do we mean by radiation? Pithy way of saying it is it's the energy that's carried off and never returns. So the next step is, how do we quantify that? Well, if we're talking about energy being transported, it's a good idea to consider the pointing vector. Which is defined, as you'll recall, as 1 over mu naught cross product of the electric and magnetic fields. It's the power, basically, that we're after, that we want to get an expression for. And that's where we calculate the surface integral over the pointing vector. Since we're interested in energy that's carried off and never returned, it may be a good idea to take our surface over which we're integrating infinitely far away, and why not make the calculation as least complicated as possible. So we'll take a sphere as our surface, and we'll make it of infinite radius. Then we want to look at each of those terms in the expressions for the electric and magnetic fields to figure out what the contribution to the radiation, what's actually going to be radiated. Well, let's consider the static terms first of all, or the static fields. First term, as I said, will collapse back to the static Coulomb field. That's going to go at least as fast as 1 over r squared. And in our expression for the magnetic field, if we consider the first term, once again, that's going to go at least as fast as 1 over r squared. So therefore, our pointing vector is going to go as 1 over r to the fourth. Now when we integrate this over the surface of the sphere, essentially I'll have an r squared from that integration over r to the fourth, and if that surface is infinitely far away, If you've got evaluating 1 over r squared at something that's very, very big, that's just going to be 0. So that's what this example tells me. Well, it tells me something I probably already knew, or probably knew intuitively, or knew explicitly, whatever. And that is that static fields don't radiate. So it has to be coming from the terms that will appear only if there is, only if there are time varying charge and current densities. So just by inspection here, I could say, well, I am going to have some radiation or contribution from the electric field that's going to go as 1 over r. And likewise, in many cases, I'll have a contribution from the magnetic field that also goes as 1 over r. So therefore, this pointing vector is going to go over 1 over r squared. And of course, when I do the integration, same as before, basically, I'm going to get some finite quantity. So those terms are called the radiation field, okay? And that is what I mean by radiation. Before I get into the nitty-gritty of calculating the fields due to an oscillating electric dipole, I do want to talk about some systems in general, okay? Now we can consider cases of point charges and the radiation that they emit when they accelerate and so forth. But for now, I'm just going to focus essentially on antennas. We'll get to the accelerating point charges later on. So when you say the word antenna, immediately, I guess probably what comes into everybody's mind is that they think of communication systems. And communication systems, radio, old broadcast television, cell phone towers, and so forth. So all those systems radiate intentionally. We can also have unintended radiation. So what are examples of that? Well, it's not just a possibility. Unintended radiation in the modern world is ubiquitous. And there are many, many examples that you can come up with. I'll just give you 3. Let's talk about circuit boards. Now, if you're a general physics, or if you're a physics student, and the only lab that you've taken is a general physics 2 lab where you put together these nice little circuits, RC circuits, RLC circuits, and at most, and maybe you've taken a class on physical electronics, possibly. You probably never were told that if you have a circuit in which there are going to be high frequency components, that those components are no longer going to act as you expect them to act. And one of the things, if you're a hobbyist, you might have read this, that if the capacitor leads are too long, and you're going to have high frequency in your circuit, those capacitor leads could act as an antenna. And if you have components acting as an antenna, which you don't want them to or expect them to, of course that's going to interfere with the operation of whatever it is you're building, and possibly could run afoul of FCC regulations, depending on how powerful you make your unintended antenna. So anyway, that's one case where you have unintended radiation. Another case is with PCB lands. And PCB stands for printed circuit board. And basically the lands are the conductors. And what happens is if you were in the business of designing complicated circuitry, and you happen to have a big loop, a big land that forms a big loop, and you've got high frequency components, guess what? Once again, that could act as a radiator, could act as an antenna. Another possibility for unintended radiation is in an AC power cord. You might be thinking to yourself, now wait a second. Juice in the United States is carried to the customer at 60 hertz. In Europe it's at 50 hertz. And you'll recall several times throughout the semester I've noted that Kirchhoff's loop rules hold exactly for DC, and they work very well for low frequency AC. And if you look at 60 hertz, well, that's very low frequency, especially when you compare that with the clocks that operate on computers. Those are in the gigahertz range. So this is very low frequency. So how in the world could it be that an AC power cord could behave as an antenna if it's only carrying 60 hertz? And the answer is it's not just carrying 60 hertz. It's carrying, there's a very real possibility it might carry very high frequency components. Or harmonics. And if it's carrying very high frequency harmonics, it will act as an antenna. So basically a lot of times, I think when, I've mentioned this before, that when you work on circuitry, Kirchhoff's loop rules work so great. And when you do the labs in general physics lab, and I would say even in physical electronics too, as long as nothing's broken, of course, everything seems like it works out just great, just Jim dandy. And you kind of get the idea that it's always going to be the case. And I guess in a way it kind of reinforces the incorrect notion about how power is transported, or energy is transported through these circuits. I touched on this when I talked about currents in circuitry in a lecture earlier in this series. And I mentioned about the importance of looking at the fields outside of the wires. So that's where people run into problems. You start thinking too much about just looking at the wires themselves and not thinking, well, the wires are actually serving as kind of like railroads to guide the fields along. So if you think about things that way, then okay, all this stuff doesn't seem so mysterious. And broadly speaking, from my point of view anyway, I would classify kinds of antennas that are used in communication systems under antenna theory, basically what you'd study if you were an electrical engineering major. And as far as unintended radiation, you would take a class on electromagnetic compatibility. And in there you discuss all the pitfalls that can arise and how to handle those kinds of cases of unintended radiation, or try to mitigate them at least, so that your whatever product that you're developing works well, and certainly no one run afoul of FCC regulations, because then that's a whole heap of trouble. But anyway, the whole thing with unintended radiation, the reason why it's or unexpected, even it's unexpected because of how people look at circuitry. You know, they're looking at the wires, and gee, if the wires are going a certain way, well, that's the way the current's going to go. And you know, you got to think outside, that there are actually fields around these components, and that's what leads to unexpected situations. Okay? So we erase this, and we will press on to actually analyzing the case of an oscillating electric dipole. Here's our dipole, and positive charge Q and negative charge Q separated by some distance d. And we'll say that this is in the z direction. Now, there's a number of different ways to proceed, and if you browse through the literature, you'll see that it seems like anything you might think of, somebody's already thought of it. So the method I found that I like the best is by Heald. And the reference to that textbook is listed on the BocaPhysics website. Some authors look at the scalar and the vector potentials, and they do expansions, they make approximations, and then ultimately they figure out what the fields are, the radiation fields are. Some people start with Yakimeno's equations, and since I like Heald's approach the best, that's how I'm going to begin. Now, the first start is how do we write these as dipole terms? Well, let's first of all look at their current density. And we can write that instead of a volume current density times a volume element there, we can write this as a current, line current, times a line element. And the current is just dq by dt. And furthermore, we know that P is equal to QD. So P is the dipole moment. So therefore, I can rewrite this as basically a P dot in the d direction over d. So it's just going to be the time derivative of the dipole moment. And by the way I've oriented this, dipole lies in the positive z direction. Okay, so now that I've worked that out, I see three terms on the left-hand side that I can evaluate. So let's look at the magnetic field first. Now, mu naught over 4 pi, and our dipole we'll assume is the center of it's centered at the origin. So we will have basically P dot cross product with the radial unit vector over r squared. And then my second term is going to be mu naught over 4 pi c. And it's the time derivative of the volume current density. So basically, all I have to do is take the second derivative of the dipole moment. So this will be P dot dot crossed into r unit vector over r. Now, the dipole moment is in the z direction, so I take the cross product of z and r. That is going to leave me with sine theta, and then I'll be in the phi direction. And then for the second term, I'll have mu naught over 4 pi c, and then I'll give me the second derivative of the dipole moment times sine theta over r, also in the phi direction. So from this analysis, this tells me that the magnetic field will only be in the circumferential direction. Now, if I look over at the electric field, I see that I've got exactly one term that has volume current density in it. So let me go ahead and evaluate that, and I'll call that E3. And that'll be a minus sign out front. I've got 1 over 4 pi epsilon naught c squared, and I'll have a factor of r. And it's the time derivative of the volume current density, so that'll mean it's the second derivative with respect to time of the dipole moment. And that'll be in the z direction. Okay, so far so good. Now I need to evaluate those first two terms in the electric field. So how do I do that? Well, what I do know is that I can, instead of having the volume charge density times volume element and doing the integration. Basically, I'm going to replace that by a charge, but there's a problem here because I can't just ignore the retardation that occurs within the dipole itself. So this is going to be a little bit more difficult problem, and isn't it always the case, than we might have expected or hoped, okay? I'm going to have to erase some of this on the left-hand side. Next way of handling this problem, which is the way field does it, is to break down the evaluation of these contributions into two components. We've chosen the dipole to lie along the z-axis. So if we evaluate the field at some point P along that axis, and then some point along this perpendicular axis, we can combine both of those components to figure out what the fields are going to look like at some arbitrary point in space. Now, the one thing is, as I said, you cannot ignore the retardation that occurs within the dipole. There is a little bit of a time lag. The distance, the time it takes for the signal to travel from here to here is equal to d over 2c, because the distance between the dipoles is, we're assuming some distance d, and so therefore from q to the origin is d over 2. And the same thing for minus q. Now it's going to take less time for the signal to propagate from here to here than it is for the signal to propagate from here to here. And we need to take that into consideration. Both of these cases, the electric field is going to be pointing in the positive or negative z direction respectively. So I'll just put a little z caret there. The first term is q, and that's going to be evaluated at the retarded time plus delta t. Remember, the retarded time is down here, all right? But the signal is propagating from here. So we're not starting from this far away, so it's actually being advanced a little bit from the retarded time. So that's going to be over z minus d over 2 squared. So this is going to have to be a little bit earlier even. So this is why we write this as q is T-Savart retarded time minus delta t. And that's over z plus d over 2 quantity squared. I'm going to expand these. So therefore this is going to be q T-Savart plus q dot T-Savart, the time derivative of q, and times delta t. charge located below the axis, negative charge. Is equal to Q minus Q dot times delta T. So I'm going to substitute both of these expansions, and of course there are higher order terms, but those are negligible. I'm going to substitute both of these expansions into the expression also. I'm going to give them a common denominator, so this will become z squared minus d squared over 4 squared. And we're going to leave off the arguments. We'll just know that they're evaluated at the retarded time. And so I'll save myself a little bit of writing here. And I'll substitute in what delta t is. So that's d over 2c. And before I proceed, I'm going to go ahead and multiply this factor out. So this will give me z squared plus zd plus d squared over 4, and then over here that becomes z squared minus zd over d squared over 4, plus d squared over 4. Okay, I'll just leave it up there just for a bit. And the question is what cancels out. We're going to have quite a few cancellations. We'll tackle the q and the q dot separately. Over here, we've got z squared and d squared over 4 terms that are going to be multiplied by q. Those are both positive. And on the right hand, for the second term, if I look at the minus q z squared minus qd squared over 4, those terms drop out. So the only surviving terms are going to be the zd terms. I'll have 2 of those. I have q zd, q zd. Now let's look at the q dot terms. And which of those terms are going to survive. This time around, if you look at q dot d over 2c times zd, look, I got minus, minus, minus. That's going to give me a minus. So those terms are going to cancel out. So therefore, z squared plus d squared over 4 terms. Here we got minus, minus, plus, minus, minus, plus. So that'll be positive. So those are the surviving terms in this case. And we're assuming that the field point is much, much larger than the dimensions of the dipole itself. So in other words, z is much, much larger than d. Since z is much larger than d, we can ignore that d squared term up in the numerator. And of course, we're ignoring it in the denominator as well. And I don't want to leave that off. We've got a factor of 2 because we've got 2 of these terms here. So those 2's will cancel out. Okay, so we've got QD over here and Q dot D, and they're both in the Z direction, so that's basically just the dipole moment and the time derivative of the dipole moment. For the contribution to the electric field from the first term along the axis is 2 dipole moment over 4 pi epsilon naught z cubed plus time derivative of the dipole moment over 4 pi epsilon naught c z squared. And I'm going to copy this over to the right hand side. That's one term down, one to go. Just leave it up here just for a bit longer. I'm not going to erase everything up here. I'll just save myself a little writing. Okay. Now we're going to evaluate the second term of the electric field. So that involves time derivative of the charge. We have an additional factor of c in the denominator, and then also it'll just be z minus d2, d over 2, and z plus d over 2 on the right hand side. And it'll both be pointing in the z direction once again. And once again, I just made a few erasures to convert the expression for the E1 axis to the E2 axis. And in fact, let me pull a factor of C out in the denominator. Substituted in for delta t is d over 2c once again. And I'm leaving off the arguments here just to save a little writing. Be aware that the charge q is still being evaluated at the retarded times. I'm looking again. At what cancels out. We look at the q dot terms, q dot times z minus q dot times d, that cancels out. Oh, what survives? Q dot times d over 2. We got 2 of those. And once again, I am going to look at the q dot dot terms. Well, it's not once again, but in similar fashion, I'm going to look at q dot dot terms. The z term survives this time around, but the d over 2 terms do not. Okay, and once again, we will make the assumption that z is much, much larger than d. Sorry, once again, I left off the factor of 2 here. We've got 2 terms here, so they add up. Okay. Doing the math here, we have in the z direction q dot d over 4 pi epsilon naught cz squared, and the second term is in the z direction q dot dot d over 4 pi epsilon naught c squared z. Now, what is qd equal to? So, what is qd? That is the dipole moment, and it's pointing in the z direction. So I can replace this by p dot, and I can replace this by p dot dot, or second time derivatives. Let me copy this over here. That's the electric field along the axis. Now, we need to figure out what the electric field is going to look like. Set as some point P. Over here. Now in this case, because the charges are equidistant from the field point, there's not going to be any difference in the retarded time. I should say the time at which the signals reach the field point. This is where it's always useful to make a little sketch in here, because we'll draw a line joining the source and the field point, and this source and the field point. Now the electric field points away from the positive charge and points towards the negative charge. So they're going to be equal in magnitude, pointing in both in the left and the right. So those two components are to the left and right. If you cancel each other out, you're going to be left with something that points straight down, and that is going to be in the theta direction when we use spherical coordinates. So the electric field evaluated at the midplane this time, the distance between this and this, say this field points a distance r away from the origin, so this is d over 2. We'll have a total distance of r squared plus d squared over 4, and that is going to be Q. And what direction is that going to be in? Well, I'll get the contribution of d over 2 over square root r squared plus d squared over 4. And that's going to be pointing in the theta direction. And let's see. Once again, we're evaluating the field at a distance much further away than the size of the dipole. So and at this particular point, theta direction is actually equal to minus z. So this is minus p over 4 pi epsilon naught r cubed. And I can do the same thing for e sub 2, but instead of actually writing everything out again, well, the only difference is if we're taking the time derivative of the charge density, we've got additional factor c, and also this is basically going as 1 over r instead of 1 over r squared. Okay, and those are your field components. Now I'm going to combine them together because it is broken down into parts. I've done basically is just combine these two by multiplying by cosine theta and sine theta. Okay, so these are the two terms I derived from E1 axis, and this is from the midplane. This is E2 axis, and this is E2 midplane. And then finally I've got E sub 3 to handle. And that is the complete electric field for an oscillating electric dipole. To put it in a little bit more illuminating form, I'm going to resolve everything, or combine all the terms that are in the radial direction, and then all the terms that are in the theta direction. Inverse cubic terms in the radial direction, we've just got one. And in the inverse square direction, we've got two contributions, this one and this one. The inverse R direction, if I look at these two terms, they have opposite signs, so those will cancel out. Now in the theta direction, we've got one inverse cubic term. One inverse square term and one inverse term. this out because it's getting a little bit scrunched up on the right-hand side. So we have 2p over 4 pi epsilon naught r cubed, 2p dot over 4 pi epsilon naught cr squared, cosine theta in the radial direction, plus p over 4 pi epsilon naught r cubed, plus p dot 4 pi epsilon naught cr squared, plus p double dot, second derivative, p the dipole moment, 4 pi epsilon naught c squared r. So what you want to notice here is that there are only two radiation terms. And in fact, in the radial direction, there is no radiation term because there's no term that goes as 1 over r. You've only got a contribution from here. So this is the radiation term. And in the magnetic field, this one is the radiation term. Okay? Some authors just give you these two terms. I've gone through all the nitty-gritty and given you everything. That's why I like Heald's approach. You've got the near field contributions, you've got intermediate field contributions, and actually for the magnetic field there's only a near and far field, there's no intermediate field for that one. Okay? Make our dipole oscillating, we'll just say that it has some amplitude p naught, e to the minus I omega n times the retarded time. Or p dot is going to give us minus I omega naught. And p double dot will give us minus omega squared, p naught. And by the way, since T sub r is equal to T minus R over C, omega t minus k times r. It's k, the wave number, is equal to omega over c. So let's substitute these terms into this expression. I'll pull out a factor of 2 p naught over 4 pi epsilon naught. Leaving with 1 over r cubed here, and in the second term, you're going to have a minus I omega, and we have an additional factor of c, but we've only got r squared there. Times cosine theta, e to the I kr minus omega t. Now I can replace this omega over c by k, in a little bit nicer form. And now for the theta direction, I'll factor out p naught over 4 pi epsilon naught. Got a 1 over r cubed term. Have a minus I omega from the for deferred trading with respect to time, and then that's going to be over CR squared, and then I've got a factor, an additional factor of minus omega squared from taking the second derivative, and that's over c squared r. So I'll replace omega over c by k, and I'll replace this omega squared and c squared by k squared. And last but not least, we'll treat b phi again, pulling out a factor of p naught. Minus I omega over r squared minus omega squared over CR. So if I throw in another factor of C, that k squared, make that k, and so I've got U naught P naught C over 4 pi minus I k over r squared minus k squared over r sine theta e to the I k r minus omega t. So those are your fields, and as I said, they contain the radiation terms, and then they contain the near field terms, and then there are also intermediate terms as well. The radial component of the electric field does not have a radiation, does not contribute to the radiation field, and the magnetic field does not have an intermediate contribution. It's just near field and far field, the radiation field. Okay? So in order to understand these a little bit better, rather than looking at these vague equations, it's useful to look at simulations. Now, Heinrich Hertz first presented these simulations, or I should say images, way back in 1888 or 1889. And it's become a teaching tool ever since. And we at BocaPhysics honor that tradition. So let's go ahead and take a look at what the electric field lines and magnetic field lines look like and snapshots during the cycle. Colors give a little indication of the magnitude of the electric field. Here's time 0. Notice that in the vicinity of the dipole, the static term dominates. As time progresses, the field lines immediately about the dipole bulge and are finally pinched off at a quarter of the way through the cycle. And once again, we see the field lines growing out from the dipole. Two pairs of loops are produced each cycle. In these snapshots, we see the transition from the near field to the radiation field. The radiation fields are spherical waves. Let's take a look at the 3D simulation, and this time we'll include the magnetic field lines. Note that the magnetic field is everywhere in a circumferential direction, except where it vanishes, including on the polar axis. Just a few magnetic field lines were plotted to give you an idea of the change in magnitude of the magnetic field. Green indicates larger magnitudes, and orange, smaller ones. To wrap this problem up, let's now look at the pointing vector and figure out how much power is actually radiated, since we're only interested in the radiation fields. And we're actually looking at the average pointing vector in this case. I'm only going to consider this term and this term. So Notice I broke my own rule about always indicating when something's a complex quantity because I left out the little tildes there, but frankly it's getting a little bit too busy on the board, so I just I left it off. Anyway, when you take the cross product of these two, this is going to be in the theta direction, and this is in the phi direction. We'll wind up with something that points out in the radial direction. Write k to the fourth as omega to the fourth over c to the fourth. So one of these c, or this c will cancel with one of these. And I can replace it over c squared by mu naught epsilon naught. So get rid of that and that. So pointing vector is equal to p naught squared mu naught over 32 pi squared omega to the fourth over c sine squared theta over r squared in the radial direction. Now when we go ahead and calculate power, this is going to essentially be, oops, that should be a, S dot n dA. We are going to have an additional factor of r squared unfortunately have to break this apart into two lines. So I've got p naught squared, the factor out in front of the integral is p naught squared mu naught omega to the fourth over 32 pi squared c, and then doing the surface interval we have going from 0 to 2 pi and the phi, d phi, and 0 to pi d theta. So we've got sine squared theta and then an additional factor of theta because of doing the integration, and then we have r squared over r squared. So the r's cancel out. It's independent of the distance. This theta interval will give you a factor of 4/3, and this will give you a factor of 2 pi. Final result will be p naught squared mu naught omega to the fourth 12 pi over 12 pi c. And that's the amount of power radiated by an oscillating electric dipole. Now there's one final quantity to calculate, but I'm actually running out of room on the board and structure anyway for you to go ahead and handle that. There's such a quantity, it's called the radiation resistance. And how that term arises is because in order for this dipole to keep oscillating and keep radiating, it has to be supplied with some power. So you want to draw an analogy between that system and also you've got a good current flowing through a resistor. So radiation resistance is found by solving this for this R, okay? And again, the factor of a half comes in because we're dealing with average quantities, okay? So that is a complete oscillating electric dipole in excruciating detail.